Hello, everybody. Welcome to my course on spherical harmonics. It's a part of my basics on geomathematics courses that I'm giving here. Spherical harmonics are a versatile tool. They are used in many cases where functions on a sphere are considered or analyzed. They are very often found in earth sciences, but you can also find it in other applications whenever a sphere plays a role or when you have, for example, a rotational symmetry. I will give you some basic introduction into this topic. Certainly, I could talk hours and hours about this topic. I will skip a lot. I will skip proofs and many other things. And as usual, I recommend you to look into literature, to look for more details, for more proofs, and all the other information that are available about this topic, because there are a lot of things that are interesting to talk about in this context. And I will only give you a little teaser on this topic. So first of all, I want to tell you what is a spherical harmonic. And before we can do that, we have to talk about something else. So first thing is a polynomial P defined on the RD into R. This is called homogeneous of degree n is some non-negative integer. By definition, if and only if you have that P of lambda x equals lambda to the n, P of x, so for every x in RD, and for every lambda in R. So if you multiply the argument of P's, or if you stretch the point x, or if you compress it, so if you extend it in direction away from the origin, you get a corresponding multiple of the original value of the polynomial, and the power of that factor that you get in front of it, the power of lambda, defines the degree of the polynomial. This is quite easy to understand. Basically, it means that, and it's really equivalent to that, that if you write down a polynomial in each of its summand, that every summand must have the same degree. So for example, a polynomial P of x, let's have x in R3, which equals x1, x2, x3, plus x2 to the 3 plus x1 square, x3. This would be homogeneous of degree 3, because whatever you add, whatever you do here, whatever you multiply the x with, if you multiply the x with a lambda, you get here lambda, 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 which gives you lambda to the 3. You get a lambda to the 3 here. You get lambda square and the lambda, you always get lambda to the 3. But if I, for example, added here another exponent, this would not be homogeneous anymore, because the last summand would have degree 4 while the others have degree 3. That's basically what homogeneity for a polynomial means. The second thing, let me put here some symbol, get some structure in that. So the other thing is that if you have a function, let's call it f, in C2, so it's a twice continuously differentiable function. D is some open subset of the RD. Then this function is called harmonic if and only if it satisfies the Laplace equation in D. Now, what's the Laplace equation? If you don't know what the Laplace equation is, or if you don't know what the Laplace operator is, that capital delta, that Laplace operator is nothing else than simply the trace of the Hessian matrix that you get here. So in RD, this would mean that Laplace F is just the sum j equals 1 to d of d2 by dxj square of f. So once again, it's a trace of the Laplace of the Hessian matrix. So you have you take all non-mixed derivatives of second order and you sum it up. Now we can mix that. We can unite that into one concept by saying, let's have a look at the set which is called harm_Rd, and let's say this consists of all functions p from Rd into R, which have the properties that, first of all, p is a polynomial which is homogeneous of degree n, some non-negative integer n, and that's the very same n that is here the index. So this index of in the name of the space refers to the degree of the polynomials. So it's homogeneous of degree n and harmonic in Rd. So it's a set of all harmonic and homogeneous polynomials of degree n. Now, I haven't talked about the sphere yet, but I should do that. So we need to talk about spheres now. And you might know there's the common notation for this particular S. So the S d-1, the so-called d-1 sphere is called the set of all unit vectors in Rd. I will use Greek letters for unit vectors. So it's all psi in Rd, which have the norm 1. I will use single vertical lines in the case of the Euclidean norm. It's the more applied version of writing that down. So the d-1 sphere is the set of all unit vectors in Rd. So it's a d-1 dimensional surface in Rd. Now, since the vast majority of all applications are given in R3, so where you have a two-dimensional unit sphere, I will restrict my attention now to the three-dimensional case. Nevertheless, everything I'm talking about can be easily extended to the d-dimensional case. And at the end of this video, I have a list of references, and I will also tell you where you find something about the other dimensions, or where you find the general theory. So I'm talking only about the three-dimensional case, the two-sphere, and I will write a capital omega for the two-sphere, so for S2 as a subset of R3. Now, how do we get everything together now? I define the space N of omega as the set of all restrictions of polynomials p in harmon omega. In harmon R3, sorry. So we take everything in our harmon R3 and we restrict these functions to omega, so we only consider them on the unit sphere in the end. So it's a set of all homogeneous polynomials of degree n, which are harmonic in R3. And after that, we restrict them to the unit sphere. We only consider them on the unit sphere. Now, if you're a mathematician, I want to stress something because this is often not really written down correctly. It's important that you talk about homogeneity and harmonicity in R3, not on omega. Why? One thing is that the degree of a homogeneous polynomial can change by restricting it to a subset like the unit sphere. Let's have a look at the simple example. So P of x for x in R3, let's say this is x1 square plus x2 square plus x3 square. That's obviously homogeneous of degree 2 because every summand has degree 2. But if you restrict it to the unit sphere, well, that's the Euclidean norm to the square, what this polynomial is. If you restrict it to the unit sphere, it's constant. It's 1. So it would be a polynomial of degree 0. So if you said now we'll talk about the homogeneous polynomials on omega, which are of degree n. This would be wrong. So it's important that you say these are the homogeneous polynomials of degree n on R3 or Rd in general, which are then restricted to omega. Well, that example is not harmonic. It's not that problematic for harmonic functions. I will say a bit more about this in a few minutes. But nevertheless, formally, it's important to distinguish that. So that's one thing, but also for harmonicity, it's important to say that the harmonicity is given in Rd before the restriction because of the Laplace operator. Remember that we require an open set here, and the Laplace operator contains these partial derivatives in every Cartesian direction. And to be able to calculate these derivatives, you need inner points because you must be able to move in every direction of space slightly away from the point where you need the derivative. If you don't have an inner point, you wouldn't be able to move in all directions. And actually, the sphere does not have any single inner point. So if you have a function which is only given on the sphere, you would not be able to apply the Laplace operator to it because you cannot calculate these partial derivatives in Cartesian directions. So that's why this is important that you distinguish that. Okay, now, once again, as a summary of that part one of the talk, is we take the homogeneous polynomials of degree n on Rd, which are harmonic on Rd, and then we restrict it to the unit sphere. And for us, it's now d equals 3. And what we get in the end, these functions, which are then collected in the space harm and omega, these functions are called spherical harmonics. And well, I could finish my talk here, could finish the video and say, have a nice day. Now you know what spherical harmonics are. But certainly there's a bit more that I could tell about this. And one thing is that we could look at the dimension of these spaces, and one can show, and once again, I will not do the proofs. For the proofs in further details, look into the literature. One can show that the dimension of harm in R3, first of all, is the same as the dimension of harm in omega, which is actually not trivial, because if you look at that example, that on R3, these two polynomials would be linearly independent, but by restricting them to omega, they would be linearly dependent. So this would be linearly dependent to every constant polynomial. So it could happen that linear dependencies get lost, that the dimension could reduce by this reduction. This is not the case, again, because of the harmonicity. And this has to do with the particular theory of elliptic partial differential equations, which one can use to prove that. But what is more important for me than this identity of the dimensions, what is more important for me now is that there is a formula for the dimension of harm in omega, and that's 2n plus 1. So we know now that if we need a basis for harm in omega, it's always good to have a basis. If we need it, we know how many functions we need. And now let's assume the following. For each n in n naughts, or each non-negative integer, let yn comma minus n up to yn comma plus n be an orthonormal basis with respect to harm in omega. With the outer inner product. Now let's clarify what this means. Certainly clear is that y and j is the spherical harmonic. Each of these y and j are certainly contained in the space. And the second thing is that they are also normal with respect to the inner product in L2 omega. If you don't remember currently what this means, it's the integral over the product calculated on omega okay for the surface element of surface integrals. I will write the omega, the lowercase omega. I know that there are many different notations for that in literature. Okay, the requirement is that they're also normal with respect to this inner product, which means if you have different functions, so if j is not k, then you must get 0, so they must be orthogonal to each other. But if it's the same function, so the inner product with itself, if j equals k, you need to get 1. That's why it's orthonormal. So this is usually abbreviated with the Kronecker delta. In case you don't know what the Kronecker delta is, this is 1 if j equals k and 0 if j is not k. So if the indices are the same, you get 1. If they're different, you get 0. So certainly we need these functions to be in harmonic. So we do that for every n. And the first index of the y just refers to the degree of these spherical harmonics. So I can already say that n is called the degree, and j, the second index, is called the order. So, so certainly they have to be in harmonomica, and I enumerate them here with minus n to n for the second index, which would give me 2n+1 functions. You also find in literature that people sometimes enumerate it with as y sub n comma 1 up to y sub n comma 2n+1. So the second index runs from 1 to 2n+1. That's also okay. This way that you have here is the what you more find in applied sciences. 1 to 2n+1 is more what mathematicians usually use. I'm an applied mathematician, so I use both. Here I use the applied version. So much about this. So we have these 2n+1 functions, and they require that they're orthogonal to each other. Now, orthogonality implies linear independence. An orthogonal system is always linearly independent. It's not vice versa, but we don't need the other direction. So we have an orthogonal system, and this is automatically linearly independent. So we have 2n+1 linearly independent functions in a vector space which has dimension 2n+1, so it's a basis. Okay, just by the number of the functions. Okay, now you might ask the question, how do I get these functions? I will give an answer to that later in this video. Let's just assume we get somehow these functions. We found a way how we can construct 2n+1 orthonormal spherical harmonics for every degree n. Now, there's something very interesting. Again, I will not prove that. Namely, if you have two spherical harmonics, let's call it Fn and Fm. So one is a spherical harmonic of degree n. The other one is a spherical harmonic of degree m. And the degrees are different. Then one can show that they are orthogonal to each other. Now this is very nice. It's very helpful because I only have to take care in my part 2 here, I only have to take care that for every separate degree, I achieve the orthogonality. So for every separate degree, I need to find 2n+1 functions, and I have to make sure that they're orthogonal to each other. The normalization is something rather easy in the end, relatively. So I only have to take care for every separate degree to get an orthogonal system. I need not take care of that if I look now at the different degrees, that they are now orthogonal to what I did before. Because that theorem, the last line here, shows me that I will get it just for free. I will get the orthogonality for free. So what I mean is, what I'm saying is, I'm just doing that now for every degree n, and I take it all together. I unite all these basis systems. So I do that for every non-negative integer n, and for every order j running from minus n to n. And this is now an orthonormal system in L to omega. So automatically, so if I take two different functions, y and j, and let's say ym comma k, and I calculate the L to omega inner product of these functions, then I know that, first of all, from that previous theorem here, that I get a delta in m, but from my definition above, I get the delta jk. So let me clarify this. So the first index refers to the degree of the circular harmonics. If they are not the same, n is not m, this tells me they must be orthogonal. So if n is not m, this is 0, the Kronecker delta is 0, and therefore the right-hand side is 0. So if they have different degrees, they're automatically orthogonal. I don't have to do anything. For getting that, it's just by theorem. But if I have the same degree, that n is m, this would be 1, then it's my job to make sure that if j and k are different, that I get 0. So I have my job to take care of this, to take care of the delta jk. So if you have two functions of the same degrees but different orders, it's my work to do that. They need to be orthogonal. For j not k, I get 0, and it's also my work to do that if j is k, that I get 1. Okay. So this is basically what I get here, what is constructed here. But there's another question that certainly arises. It's an orthonormal system in L to omega. If you know a bit about functional analysis, you know orthonormal systems are usually complete in a certain space, which means that you can expand every element of that space into these functions, into these elements of the orthonormal system. So the question is, in which space are they orthonormal? Or to put it in a different way, how many functions can we represent in this orthonormal system? Can we expand in this orthonormal system? And the other answer is very, very nice, very helpful. Namely, this system would be number 4 now, yeah, that this system of all y and j this is a complete orthonormal system. You can equivalently say it's an orthonormal basis, a complete orthonormal system in L2 omega, certainly with respect to the L2 inner product. By definition, it means if you have an L2 function which is orthogonal to every y and j, then this function can only be the 0 function. That's a mathematical definition, but there are some equivalent statements which show you how useful that is. And one of that in particular is that for every L2 function on omega, you know now that this can be expanded into a series of these spherical harmonics. So I get the L2 inner product of f and y and j multiplied by y and j. It's actually just the projection of f into every direction, where the direction is a function y and j. So this is people call it an orthogonal series. You can also call it a Fourier series. Certainly Fourier did something else. Fourier discussed the expansion into the trigonometric polynomials of sine n t and cosine n t. But on the other hand, I told you that you can look at circular harmonics in different dimensions, and you can also go one direction below. Look into R2. The unit sphere in R2 is unit circle. And unit circle, functions on the unit circle are nothing else than functions which are 2 pi periodic. Because if you go once around, you can parameterize the circle with the angle. And if you go once around it, you have to end there where you started. So you need 2 pi periodic functions, and they can be expanded into the classical Fourier series. So this is just closely related. It's just one dimension higher. Or in general, if you do that in RD, you can say this, the spherical harmonics expansion in RD is just a generalization of the Fourier series by d equals 2, where you're in 2 dimensions. Okay, so it's a Fourier series. Let me write it down. Fourier series. There are some other things maybe I can mention that too. For example, if you have two L2 functions, then you can write the L2 in a product. By a series which involves the so-called Fourier coefficients or the Fourier transform. It's also where how these the nomenclature of that these coefficients are. So I'm only talking about real valued functions here, by the way, because if they're complex valued, you need a complex conjugate of that. There's also a theory for complex valued for harmonics. It's very similar to what I'm doing here. You need some complex conjugates at some parts, and I won't skip this here. So the latter one is called the Parseval identity. Okay. So, but the most important thing is certainly this Fourier series that we have, which means that every function, every L2 function on the unit sphere, and that's a very weak condition, because it only means that the integral over the square of f on omega gives you finite value. So that's very simple. The function after even doesn't have to be continuous for achieving that. It doesn't need to be continuous for achieving that. So it's very simple to achieve. It's many functions satisfy that. And that's why this is very often used in practice. And for example, a lot of data, for example, in earth sciences, are just submitted or made available in the internet in databases by just giving you these coefficients. So there's a particular system of the y and j. I will soon talk about that. And then they say, okay, we know that's the system of y and j that I'm using. And here are the coefficients of our expansion up to a certain degree, and you can download that. So this is a common tool. It certainly has some pros and cons, but this is something that you definitely have to know about because it occurs in many occasions. Okay, so that's why it's so important. That's why many people use it. Now there are some more things that are worth to know. And one thing is something that for that I have to look at the Laplace operator once again in R3, and more precisely I have to look at polar coordinates. Now I have a separate video on polar coordinates, but that's why I will only briefly talk about this. If you have a point x in R3, you can represent it in polar coordinates by some r square root of 1 minus t square cosine phi, r square root of 1 minus t square sine phi, and rt. Now, you might not necessarily know it in this way. What you, for example, might know is that t is represented by a cosine theta, where theta is in between 0 and pi, and is called the latitude. And phi is, for example, in between 0 and 2 pi, and that's the longitude. Now, there are some variations. Some people represent t by sine theta, where theta is between minus pi over 2 and plus pi over 2, and phi could also be between minus pi and pi. For example, more about this in my video about polar coordinates. So I will use that system, and the transfer between the different systems is rather easy. Now, the Laplace operator, which once again is a trace of the Hessian matrix, So it's d by the x1 square plus d2 by the x1 square plus d2 by the x2 square plus d2 by the x3 square in 3 dimensions. You can represent it in polar coordinates away from the origin. So if r is not 0, I could say that the r is in r0 plus, and that's certainly the Euclidean norm of x. So the representation of the Laplace operator in polar coordinates is d2 by the r square plus 1 over r, plus 2 over r d by the r plus 1 over r square times an operator which only acts on the angles, I will write just indices t and phi. I will give you the precise formula soon. At the moment, it's just important to know this acts on the angular variables. So we have a kind of a separation. This only acts on the radial variables. So the differentiation only acts there. And this differentiation only acts on the angular variables. And this latter one here, that is called the Beltrami operator. Sometimes it's also called the Laplace-Beltrami operator. Okay. So now, why is that important? Because you can ask a question, which is, what are the eigenfunctions of the Beltrami operator? So I'm looking for something, that's first of all, I'm looking for a function f in C2 of omega, or the Beltrami operator contains derivatives up to second order. F should not be the zero function. And a real number lambda, everything is real valued in my case, such that Beltrami applied to F gives you just lambda times F. So, and F is then called an eigenfunction. If you're not familiar with that word, you might know what an eigenvalue is and an eigenvector is. An eigenfunction is just an eigenvector in the case that the vector space is a space of functions. Okay, that's all. And lambda will be the eigenvalue. Now, this is already solved. The eigenvalue problem of the Laplace operator is an old question. And what we know is that the only eigenvalues are discrete, or they're given in the following way. So if lambda is an eigenvalue, there must be a non-negative integer such that lambda has the form minus n times n plus 1. So lambda actually consists of very particular negative integers. Namely, those of the form integer times next integer. Okay, minus n times n plus 1. So that's one thing. These are the only eigenvalues of the Laplace of the Beltrami operator. But we also know what the eigenfunctions are, what the eigenspaces are. Namely, if I have that particular eigenvalue minus n times n plus 1, then the eigenfunction must be a spherical harmonic of degree omega, of degree n on omega. Now, since I assume that it's an eigenfunction, so it must not be the zero function, have to take out the zero function here as well. Okay. So what is important now is that equivalence, because this gives me an alternative way of defining spherical harmonics. So instead of saying a spherical harmonic is a homogeneous polynomial of degree n, which is harmonic both on R3 and which is then restricted to omega, instead of saying that, I could say a spherical harmonic of degree n is an eigenfunction of the Beltrami operator to the eigenvalue minus n plus 1. That's the same. It's just equivalent to each other. Okay, now you could say, well, that's something interesting for mathematicians. They can prove nice things. So what does it help me if I'm an applied scientist? Well, it helps you a lot because that's the way how you can construct a particular basis. Because solving that eigenvalue problem gives you a way of finding particular spherical harmonics, and this also gives you a way of finding an orthogonal system. Let me show you how this works. So that's part 6 of of my presentation here. So first of all, the Beltrami operator of f, I will write this now as a function depending on the unit vector xi, and xi will be given in polar coordinates t and phi. So the Beltrami operator applies to t and phi. And let me show you how this is done, what this looks like. So you first get d by dt of 1 minus t square df by dt. I will skip the xi t phi on the right-hand side, plus 1 over 1 minus t square d2f by d phi square. Okay, that's the Beltrami operator. And what I want now is that this should be lambda f. Okay. Or more precisely, lambda should be minus n times n plus 1. Okay. Maybe something I could mention about this, because if you look at this operator here, this part which only acts on t, you can apply it certainly also on a 1D function. You can apply it to a function which depends only on one variable. This operator is then called the Legendre operator. You might know maybe the Legendre polynomials, and the Legendre polynomials satisfy a particular differential equation, the so-called Legendre differential equation. And if you have a closer look at this differential equation, you will observe that this differential equation is again an eigenvalue problem, namely the eigenvalue problem for this Legendre operator. So the Legendre polynomials are eigenfunctions of this Legendre operator, and the Legendre polynomial of degree n is an eigenfunction of this operator to the eigenvalue minus n times n plus 1. There's a very close relationship between spherical harmonics and the Legendre polynomials. I will just add this as a comment here, because if you sum up here products of spherical harmonics of the same degrees, so I'm running here through a system, y and j running from minus n to n. I'm multiplying two such basis functions and I evaluate these at two arbitrary points on the unit sphere. Then I get 2n plus 1 over 4 pi times the Legendre polynomial at xi times zeta. But this is true for all xi and eta in omega, and Pn is the Legendre polynomial of degree n, and this is called the addition theorem. For spherical harmonics, I will abbreviate. Okay, just as a comment here, because I think this should also be mentioned, that additional theorem it's an important tool in spherical analysis. So it's coming back to our eigenvalue problem on the sphere, not the Legendre eigenvalue problem, the eigenvalue problem of the Beltrami operator. Now, there's one thing, namely that we have a separation here. We have one summand which only consists of derivatives with respect to t, and we have another summand which only consists of derivatives with respect to phi. And this motivates a so-called separation ansatz. So we'll look for functions which can be written as a product of a function of phi and a function of t. So thirdly, this will not give us all solutions, but we're just looking for 2n plus 1 orthogonal solutions. We don't need all solutions. And this is really helpful. So why is it helpful? Because I can apply now the Beltrami operator to that function. So I have to go through that. Let's have first a look at the Legendre operator. This is certainly a case for the product rule. And I will do the uncommon way and first apply the derivative to that. So the product rule gives me, first of all, 1 minus t squared unchanged times the second derivative of f. Okay, so it's 1 minus t squared. Let me already write 1 minus t squared. And then multiply with the second derivative of f with respect to t. So if I multiply, if I differentiate that with respect to t, it only applies to h. So I get g of phi and then the second derivative of h. Okay, so this is the first term of the product rule, or the second if you wish, the 1 minus t squared times this differentiated, and I get another term from the product rule. I'm still here, and now I have to differentiate this here, and I get minus 2t, and then it's only the first order derivative of f with respect to t, and that certainly gives me g of phi h prime of t. Okay, plus, now I'm here, and now it's the opposite way. This only applies to phi, so I only differentiate with respect to phi, and this certainly only applies to g here. So I get here plus 1 over 1 minus t squared, and the g double prime of phi h of t. And the eigenvalues problem tells me it should be lambda g of phi h of t. So what I want now is a separation of the variables in my equation. So I want to take everything with a t to the left-hand side and everything with a phi to the right-hand side. And I do that, first of all, by dividing actually by f. So I multiply with 1 over g of phi h of t. Now, I have to do that away from the zeros of f. Now, first of all, I don't want f to be identical to 0. I don't want it to be the 0 function because I'm looking for eigenvalues. And it would also not be helpful for finding a basis to take the 0 function. So I would have functions maybe most likely with some zeros. So I have to do that away from the isolated zeros of the functions that I'm looking for. But since I'm looking for continuous functions, it's not a problem that I have isolated points where I don't have identities anymore, because due to the continuity, I can easily extend it to the missing points. So I'm dividing by g and g times h here, and this is not very difficult. So first of all here, let me first start with the 1 minus t squared. And if I divide that by g, if I divide that by gh, the g would cancel out. So I would simply get h double prime of t divided by h of t. Okay, then I'm coming to the next term. I get, first of all, minus 2t. And I divide this by g times h. Again, the g cancels out. And I get an h prime of t divided by h of t. Now I will put the next term already on the right-hand side. So I get here minus 1 over 1 minus t squared. And now if I divide this by gh, now the h cancels out, and I get g double prime of phi divided by g. Now you might guess why I put this on the right-hand side. And I will put this on the left-hand side because I will know where I'm going to later on, that this will be helpful later on. So I will put this on the left-hand side. And don't forget that I'm dividing by gh, so I have simply a lambda left. Or maybe I can already use what lambda is. Lambda is minus n times n plus 1. So I can write here a plus n times n plus 1. Okay, for some n that I've chosen. So still, the variables are not completely separated because I have a t dependence here on the right-hand side. This is why I multiply the equation now with 1 minus t squared. And this gives me 1 minus t squared to the square, h double prime of t by h of t, minus 2t, 1 minus t squared, h prime of t, divided by h of t, plus n plus 1 times 1 minus t squared, and that equals minus g double prime of phi divided by g of phi. Okay. Now, I use the separation ansatz, as you know, and actually there is a standard procedure if you use the separation ansatz. First of all, you always make such kind of an assumption. You're looking for a function which consists of a product of terms which have different dependencies on variables, which do not have common variables. Now, if you do that, if you insert it into your differential equation, then the partial derivatives turn out to be ordinary derivatives, 1D derivatives, as it was the case here in my differential equation. Then you separate the variables to take everything with one variable on one side of the equation, everything with the other variable on the other side of the equation. And all that you're doing here has one single purpose. You want to do now the following argument, the following implication that I'm doing here. And that's always the purpose, that's always the target of all the separation ansatz. Because now, since I've separated this, I have everything with t on the left-hand side and everything with phi on the right-hand side. I can say the following. Let's assume I enter a particular value for phi, whatever it is. Say phi is pi or so. So I enter a particular value for phi on the right-hand side. This gives me a particular number that I got on the right-hand side. So I have a fixed value for phi, a fixed value therefore on the right-hand side. Still, the equation says it's true for all phi and for all t, which means I can enter every value for t, for -1 to 1 actually, I can enter every value for t on the left-hand side. It must be equal to the right-hand side, no matter what I enter for t. Well, if I do not change phi, the right-hand side doesn't change. But if I change t, the identity requires that the left-hand side mustn't change either. And vice versa, if I enter a particular value for t on the left-hand side, I get a particular number on the left-hand side, and no matter what I enter for phi, the right-hand side must not change because it must be always equal to the value that I get on the left-hand side. So as a consequence, changing t is not allowed to change the whole term, and changing phi is not allowed to change the whole term that occurs here, which means both sides have to be constant. So this is equal to, I will call the constant mu. Okay. Now I will take this, I will copy that to the next page. Okay, this gives me two differential equations. Or maybe I have already enumerated with numbers. Let's say A. I will start with the easy one, g double prime of phi equals minus mu times g of phi. And the other one, which is definitely more ugly, gives me 1 minus t square to the square h double prime of t. So I'm multiplying with h of t now, as I multiplied the other equation with phi. So minus 2t, sorry, minus 2t, 1 minus t square, h prime of t, plus n times n plus 1, 1 minus t square, h of t equals mu times h of t. Okay. Now you can collect this here, you can put this on the other side if you wish, but that's not important now. So I will tell you a bit more about solving A. I will not tell you so much about solving B, because this would extend my video essentially. So let's talk about A. Now, that's very simple. If you're familiar with ordinary differential equations, you know that this is an easy equation. It's a linear equation, order 2, and in particular, linear with constant coefficients. For that, it's a very simple procedure of solving that. It's actually just a simple recipe that you have to apply. And this turns out that it depends on the sign of the coefficient on the right-hand side. Depends on the sign of mu. So there are three cases. Let's call it lowercase a. One case is that mu is negative, which gives me actually here a positive coefficient. If you do that, you find out g of phi must have a form of, let's say, constant 1 times e to the square root of minus mu phi plus constant 2 e to the minus the square root of minus mu and phi. Okay. Now, how do you get the constants? Usually, in case of ordinary differential equations, in particular in lectures, where everything is quite academic, you say, yeah, we need two initial conditions. We don't have that here. So, because there's nothing coming up with an initial condition, but we have a different condition because phi is the longitude. It's longitude. It's it's running from, if you read, in my case, it's 0 to 2 pi. You might also refer minus pi to 2 pi, whatever it is. It is an interval of a length of 2 pi. Now it's a longitude once again. Let's say phi equals 0 represents the Greenwich longitude. Then you're going around the sphere, and at 2 pi, you're back at the Greenwich longitude. So phi equals 0 and phi equals 2 pi represent the same geographical longitude on the sphere. So they must be the same. So which means we get immediately conditions to our G, namely at 0, you must get the same than you have at 2 pi. Well, actually, we want eigenfunctions of a differential operator of second order, so it doesn't suffice to have it only for G, only definitely for G prime the same. And wouldn't I also need it like that here? But no, I don't need the latter one. Why don't I need it? Because if you look at that, if you insert, let's say 0, G double prime of 0 is minus mu times G of 0. Okay? G double prime of 0 is minus mu times G of 0. But G of 0 is G of 2 pi. So G double prime of 0 is mu of G of 2 pi. But G of 2 pi gives you something about G double prime of 2 pi. So if you have a closer look at that, you see that the equation already gives you that if you know this for G, by inserting that, you certainly get automatically that G double prime at 0 also must be G double prime of 2 pi, because it's just a multiple of G at 0 and 2 pi. And now if you differentiate that equation, you get that the third derivative of G is minus mu times the first derivative of G. And this shows you that that automatically implies you that the third derivative has the same condition. Third derivative of 0 at 0 is automatically the third derivative at 2 pi, just because of that and this. And then it's a simple induction, a simple iteration to see that then every derivative of G automatically satisfies that condition. So we really only need these two conditions. Now, if you insert this, I will not do that in detail. It's practical and not very exciting. If you insert that into the solution, this general solution for G, sorry, you get two linear equations for two unknowns, C1 and C2, which are very easy to solve. Namely, C1 is C2 is 0. That's the only solution that you get in the end. Okay, now that's not very nice, because it means that G is identical to 0. And since my F that I'm looking for actually is G times H, F would be 0. Remember that. Well, that's how I started all that here. With the separation ansatz that I was using here. So if G is identical to 0, F is identical to 0, I would get a 0 function. And once again, this is not useful for finding a basis. So let's continue our search. Now, if mu is 0, you get a different solution. It's very easy. If mu is 0, the equation is G double prime is 0, which means G is a polynomial of degree 0 or 1. So it's Z1 pi plus C2. Now, let's have a look at the first condition. G of 0 is G of 2 pi, which means G of 0 is obviously C2. And this is supposed to be G of 2 pi, which is C1 times 2 pi plus C2. Now, if you look at this equation here, you can easily cancel out C2, and then C1 2 pi needs to be 0. So this gives you, if you cancel, if you separate, if you divide, sorry, if you subtract C2 on both sides, you get 0 equals C1 times 2 pi, and therefore C1 is 0. Now the second derivative, the second condition is not helpful, because G prime of phi would be simply C1, and that's 0, and that's certainly the same at 0 and 2 pi. So I get one solution, namely G of phi, or let's say G is constant. This is a possible solution. For mu being 0, you can get this here, that this equation gives you that G is a constant function. Okay, now the third case, still missing that, mu is positive, which means I have a negative coefficient here. And again, by looking at the theory of such differential equations, you see that there is the following general solution: a constant times the sine of square root of mu times phi plus another constant times the cosine of square root of mu times phi. Now, this is a bit more lengthy to look at the conditions here. Again, first of all, similar to the case that we had here, if you write down these equations here, you get a system of linear equations, a system of two linear equations for the two unknowns C1 and C2. Okay, sorry, there's no multiplication here. There is a multiplication, there's no addition. Okay, so you get a system of two linear equations for the two unknowns C1 and C2. Okay, so much about that. Now, what you get in the end is a system of linear equations with a matrix, a 2x2 matrix. And again, I don't want to get the zero function as a solution. So I don't want C1 and C2 to be 0, because this gives me a zero function. It's not helpful for looking for a basis. What does it mean? It means I need to get a solution of the 2x2 linear equation system, a solution which is non-trivial, which gives me C1 and C2 not being both identical to 0. So you have to look at the determinant of that matrix. And then you find out that there are indeed cases where that determinant is 0. So if the determinant of the matrix is 0, it tells you that this quadratic matrix is singular, and therefore you can have non-trivial solutions. So let's say non-trivial solutions. And that's now interesting, if and only if mu is, or let's say if square root of mu is a positive integer. In other words, if mu has the form j square or a positive integer j. So that's now very helpful for looking at our basis systems, because we only need, remember that we only need two n+1 functions, and by having a closer look, you find out that there is a way of reducing the functions g. I will call it g sub j of phi, and you can choose it, for example, as sine of j phi. Remember, it's here the square root of phi mu, which would be the j again, and that's for j equals 1 to n, and the other one would be cosine of j of phi, for j equals minus n up to 0. So that's certainly one way of doing it. You can also take the sine j of phi for j running from 1 to 2n+1. It doesn't matter. I need 2n+1 functions, first of all. And be aware of that. I was hiding something here. Namely, I had this case mu equals 0 with the constant function, and that's hidden here in the case j equals 0. If that's 0, the cosine of 0 is just 1. So the constant case is hidden in that construction. And that's now very helpful, because remember our separation ansatz, and remember something else that we were talking about before. If I now have a function integrate over omega, a h dj, I will skip the arguments here because it doesn't fit up properly, and then h g k, the omega. So usually if you calculate the integral, you would separate it into the two parameters for the sphere, which would be t and phi, or theta and phi. For t, it's a bit easier because you don't get another surface element there. You get a -1 to 1 dt, and you get a 0 to 2 pi d phi. Now this maybe is a bit too close. Okay. So then I would get an h of t, gj of phi, and then h of t, gk of phi. And then you can split this up into integral -1 to 1 h square of t dt, and integral 0 to 2 pi gj of phi, gk of phi d phi. And it's now very simple. It's actually a simple exercise in integration by parts to calculate these integrals that occur here. You must consider the case where you have a sine with the cosine function with maybe with different parameters, but also you have to take the case two different sine functions with different j's and two different cosine functions with different j's, and then you find out actually if you don't have the same functions, they're really orthogonal with respect to the L2 inner product on 0 to pi. That's what we have here. So this is in fact here 0 if j is not k. So if it's the same, you get a normalization factor, which is usually something like pi or 2 pi, depending on the j and k. But it's also easy to calculate. And again, a simple example, simple exercise for integration by parts. So I've done my job, because my job was finding for every n. Actually, I've almost done my job. The job was finding for every degree n a system of 2n plus 1 orthonormal functions in Harman omega. And I have now just found out, okay, by choosing the g sub j of that kind, I can guarantee, at least for the phi part, that the phi part satisfies everything that is necessary to get a spherical harmonic. And I already have the orthogonality guaranteed by choosing these factors. Now, I've almost done my part, because there's the h function still missing. So the h function is not important for the orthogonality, but still h needs to satisfy the differential equation. And this makes it a bit more complicated, because on the one hand side, it's a bit more complicated here. You have a bit more, it's a bit ugly. It's linear second order, but with non-constant coefficient, which is much more complicated to solve. And the other thing is that there is the mu in there. And the mu is my j square. So it's not as it is the case here, as I showed it here, because actually in reality, you would have a hj and an hk here, because if you have a different function g, then the different function g here corresponds to a different parameter j. So it solves the differential equation or that differential equation here for a different mu. So if j, for example, if you compare g1 and g2, g solves that equation with -1 there, and g2 solves it with -4 in front of that. So for mu equals 1 and 4, and therefore for h you will have once the equation with the 1 and once with the 4. In general, you have the j square here. So for different j, you get a different equation for the h, which you have to solve. And this is a lengthier thing. I would have to write several pages for telling you how this works. Again, you have more than the necessary number of solutions that we need to get our basis. actually for every j, it's enough to get one factor in front of it. But this is a well-known theory, and I will just show you how this ends, what the result of this actually is. This is the common system of spherical harmonics basis functions that occur in practice. You recognize here the g sub j functions, as I called them, the trigonometric polynomials with respect to the longitude, and the solutions of the h functions, as I called them, they are so-called associated Legendre functions. It's a well-known system because the spherical harmonics are important. Many people have talked about that and discussed that and wrote papers and books about that. So there were a lot of formulas about this. So they're called, once again, the associated Legendre functions. Look into the literature for more details. And for normalizing them, you have to do a bit more work. And as you see, this, you're getting some, again, not a very nice factor here in front, which makes sure that you get an orthonormal system, a system with a norm 1. But the orthogonality for every degree n, or a fixed degree n, is already given by these trigonometric polynomials in the end. And since they are spherical harmonics, they're different. They're orthogonal to each other for different degrees. So this is the common system that you find as orthonormal basis systems. It might differ in the way the orders are enumerated, and some people normalize it a bit different. That, for example, that the norm is not 1 but 2 4 pi or so. But with the exception of a few minor differences, this is what commonly is used when coefficients of data sets in spherical harmonics are calculated. And I want to show you some plots of spherical harmonics of degree 5. So we have 2 times 5 plus 1, that is 11 functions in that basis. And I start with order -5. So you get a cosine function, cosine of -5 times phi, which is the same as cosine of 5 times phi. So you get a corresponding number of maxima and minima, let's say traveling around the sphere. You have not very much structure with respect to the latitude. That's because of the associated Legendre functions. Basically, it's a derivative of a polynomial of degree 2n, which is differentiated n plus j times. There's something else. There's some other term with a square root in front of it. But if you have a polynomial of degree 10 in that case, and if you differentiate it actually 10 times here, because n plus absolute value of j more precisely is 10. So it's just a square root of 1 minus t squared, something that kind that occurs here. So you get a very simple structure here in the latitude. Now, if you move to order 4, you get this case here. Now you get more structure in the latitude. So this polynomial of degree 10 is only 9 times differentiated. And in the longitude, I have a cosine of 4 phi. Let me continue to the next order, -3. I get a cosine of 3 phi, and I get more and more structure in the latitude. And this continues to order -2. It's now a cosine of 2 phi. You get essentially more or less maxima and minima in the longitude direction, but you get more maxima and minima in the latitude direction. And for order -1, that's the way it looks. And for order 0, now that's interesting because remember for order 0, that was the cosine of 0 times phi. That was the constant solution that we obtained for G. So we don't have a phi dependence. And this is important for some applications. For example, if you have a rotational symmetry with respect to the rotation axis, and that's, for example, the case if you look at the gas giants like Jupiter and Saturn. People who model that usually assume an independence of phi, and this implies that modeling fields on these planets only take the yn, 0 functions into account. And now for order 1, this is just going the opposite direction. The structure in the the latitude becomes now again less complicated by I'm getting maxima and minima in the phi direction, which is now order 2. It's just a sine function instead of a cosine function that occurs here. So this is how this becomes now again. And that's very simple. If you compare that to order -5, you simply see, sorry, where is it? You simply see a shift in the shift in the longitude, a phase shift. And I can't say that often enough. No internet video can replace a good textbook. So that was just a little teaser on spherical harmonics. Please look into books, read more about that. They have much more information for you and much more places / time for explaining it to you. And I will have you a very small selection, which is by far not complete, of our literature that you can have a look at. I want to start with the last one in the list by Klaus Müller, which is from 1966. It's a very actually small book on spherical harmonics that, for example, discusses the general d-dimensional case, but you find all basic formulas on spherical harmonics in that little thin book here. The case of arbitrary dimensions is also discussed in that book here, spherical harmonics in p dimensions. It's a more recent book, and it's a bit longer, has a bit more pages than the book by Müller. So both are very valuable resources if you want to know more about that. Now, Willy Freyden wrote a lot of books on mathematical tools in earth sciences, and in particular also on function systems on the sphere. There are also not only scalar spherical harmonics, there are vector spherical harmonics and tensor spherical harmonics. And I have a selection of 2 books by Willy Freyden and co-authors, which I can also warmly recommend if you want to know more about spherical harmonics, but not only about them, but also in other approximating structures on the sphere. And last but not least, the sphere is only a particular case of an ellipsoid. There is also a general theory on ellipsoidal harmonics, sometimes also called Lamé functions. And there's a nice book by George Dacios, which I can recommend on that, which gives you basically the state of the art on ellipsoidal harmonics, much more complicated theory than spherical harmonics. And if you wish, you're certainly also welcome to look into my books, where I also give information about a lot of approximating structures on the sphere. And there's certainly also a lot about spherical harmonics in 3 dimensions or in the 2 sphere that you can find in these books. So that's all. I hope that you learned something in that video. I hope that this became interesting for you. Or maybe you came across spherical harmonics in some context and you wanted to know more about that. I hope that I could be helpful. And maybe also the references that I gave you can be helpful for you. So I hope you enjoy my videos. Maybe you want to look into some of the other videos. And I'm certainly grateful for every constructive feedback that you can give to these videos. Okay, thank you very much for listening. Thank you very much for staying here until the end. And maybe you will see me in some other videos. Bye-bye.